Okay guys, we are in 11.4. This is our next to last section of the semester that we're going to cover, and we're talking about mathematical induction. I expect that this is probably new to everyone. This is kind of a proof methodology where you are showing that certain conditions are true to show that your statement is going to be true for all natural numbers. Now notice that mathematical induction applies for all natural numbers. Our natural number set is our set of counting numbers. So it's our positive integers, not zero. Think about when you learn to count as a child, where you start. Well, you start with 1, right? And you count discrete things. So you count 1, 2, 3 cookies, or 1, 2, 3, 4 toys. But this is our set of natural numbers. Now when we are using the mathematical induction theorem, we have to show that two conditions are satisfied with regard to any statement about natural numbers that we are trying to show true. Our first condition is that the statement is true for the natural number 1. For the natural number 1. So first we have to show that whatever we're trying to prove is true when n is equal to 1. Then our second statement says that if the natural number is true for some number k, it's also true for the next number, k plus 1. So if the statement is true for some natural number k, then it is also true for the next natural number, k plus 1. Now think about this like knocking down dominoes, alright? If you knock the first domino down, if they are set up within reach of each other, you knock the first domino down, you can expect that it's going to hit the next one and knock it down, and that one will knock the third one down, etc., etc., etc. So if we assume that if it works for one, and then we say, okay, we've got any natural number k, and it works for that, then we are going to show that it works for the next number in line, and that would prove that it's going to work for the next number after that, etc. Okay, so let's do a couple of examples. I'm going to warn you, we're going to change our third example and add in one. So we can kind of get the feel for this. I'm not exactly sure, I haven't gone back yet to see exactly what the my math lab homework looks like. If you're struggling with what the inputs are on the My Math Lab homework, I encourage you to use the Show an Example option so that you can kind of walk through and see what steps they are after on the problems given on the homework. There's not very many. I think there's like 6 or 7 My Math Lab homework problems for these. Okay, so we're going to show that this statement is true for all natural numbers n. And the statement we are given is 1 plus 3 plus 5, and then we are going all the way to 2n minus 1, and that sum is going to be equal to n squared. So what is it that we're doing here? Well, 1, 3, and 5, those are odd integers. So what we're after is showing that the sum of the odd integers is going to be equal to n squared. So our statement shows that the sum of the odd integers is equal to n squared. One way to kind of understand this and to kind of think about problem solving is to think about smaller problems. We haven't defined a set endpoint for n, so let's do some examples for this first statement. For example, if n is equal to 1, then I would have just 1, that's one odd integer, and that's equal to 1 squared. What if I have 2 odd integers? N is 2. Well, my first 2 odd integers are 1 and 3. 1 plus 3 is 4, and that's equal to 2 squared. If I have 3 odd integers, that would be 1 plus 3 plus 5. Well, that sum is 9, which is 3 squared. So we're good so far. If I kept going, if I have 4 odd integers, I would have 1, 3, 5, and 7. and that sum is 16, which is 4 squared. So you can see that it looks good, right? If I add 4 odd integers together, their sum is 4 squared. So we suppose that, for example, if I added 8 odd integers together, their sum would be 8 squared, or 64. We don't have time to check all of them, so we want to see if our induction theorem holds true. Well, we're going to start with the first statement. And we're going to see if it is true. Is it true for n equals 1? Is it true for n equals 1? Well, if n equals 1, then I take that general case, 2n minus 1, and I need to see if that equals n squared. If n is 1, I have 2 minus 1 is 1, and 1 is equal to 1 squared. So yes, it is true for our first condition. That satisfies the first condition. Excuse me. Okay, so now we're going to come over here and we're going to say, all right, the next thing is that we're going to assume that it's true for some natural number k. So we are going to assume that 1 plus 3 plus 5 all the way to 2k minus 1 is going to be equal to k squared. I'm assuming that. The second condition is, if this is true for some k, then it is also true for the next natural number, k plus 1. So let's look at the next natural number, k plus 1. Well, that would look like 1 plus 3 plus 5 plus ... I get to that 2k minus 1, and then the next natural number would be 2 times k plus 1 minus 1, and that would be equal to k plus 1 squared. Okay? Well, this is that previous statement that we already said was equal to k squared, right? So we said that this is equal to k squared. And then if I simplify in here, I get 2k plus 2 minus 1, and then I've got it equal to k plus 1 quantity squared. Well, 2k plus 2 minus 1 is 2k plus 1. So this side is k squared plus 2k plus 1. And that is equal to k plus 1 quantity squared. Let's FOIL that. If we FOIL it, we get k squared plus 2k plus 1. Look at that. Those sides are equal to each other, so our second condition holds. So this statement is true for all natural numbers. Okay, so we used substitution. We made an assumption and we said, you know what? This is equal to k squared. We're assuming that. So then I can take that back out and I can replace it with k squared. Let's do another. We're going to start with our first statement, our first condition, show that this statement is true for all natural numbers n. So I'm starting with 18, 36, 54, so I'm adding these numbers, and notice that these are multiples of 18 plus 18n. So I'm going to this last multiple of 18, 18n, and that sum is going to be equal to 9n times n plus 1. That's what we're trying to prove true. Our first condition, we need to check to see, is it true for n equals 1? Well, if it's true for n equals 1, then this piece is going to be true for n equals 1. So we would have 18 times 1 equal to 9 times 1 times 1 plus 1. 18 times 1 is 18. This is 9 times 1 times 2. That is also 18. So our first condition holds. Our first condition is true, and we can move on to our second condition. For our second condition, we have to assume that we can replace n with k. So I would have 18 plus 36 plus 54 all the way to 18k, and that would be equal to 9k times k plus 1. So that's my assumption. Okay, so if it is true for k, my condition 2 is that if it's true for some k, then it is going to be true for k plus 1. So I'm going to take it one more step. I'm going to say, all right, I have 18 plus 36 plus 54 all the way to 18k, and then I can also say 18k plus 1. And if I replace k with k plus 1 on the left, I also do so on the right. So that side would be 9k plus 1 times k plus 1 plus 1, because k plus 1 plus 1. Okay, what have we got here? Well, this is my assumption, that previous part right here. So I can substitute in 9k times k plus 1 for all of this. And then I have plus 18k plus 18. And on the right, if I distribute, I have 9k plus 9 times k plus 2. Okay, so on the left, when I distribute here, I get 9k squared plus 9k plus 18k plus 18. And when I combine that like term, I'm left with 9k squared plus 27k plus 18. And I need to work and FOIL this on the right, which gives me 9k squared plus 18k plus 9k plus 18. And look at that. That is exactly what I had on the left. So my second condition holds true. And we have used our induction theorem to show that this is going to work. Okay, let's look at our next example. Now, like I said, our next example is not the example we are given. This is a fine example, but I struggle with it a little bit, and so I'm not going to explain it to you on video without you available to ask me questions about it. I think that's not fair. So we're going to do a different example. The example we're going to do, we are going to show that 1 plus 2 plus 3 plus all the way to n is equal to n times n plus 1 over 2. So basically, I'm adding my natural numbers, and I want to show that the sum of my natural numbers is n times n plus 1 over 2. So we're going to make sure that we prove both of our conditions are true. The first condition, we need to show it is true for n equals 1. Well, if it's true for n equals 1, then n, we just have the first number. We don't have all of this. It's just 1, will be equal to 1 times 1 plus 1 over 2. So we have 1 is equal to 2 over 2, and 2 over 2 is 1, so our first condition is met. Next, we assume, since it works for 1, we assume that it is going to be true for some natural number k, so that we have 1 plus 2 plus 3 plus k. That's going to be equal to k times k plus 1 over 2. We assume that that is true for k. That's what we've been given. Now, if that is true, I can take the next step and show it is true then. If it's true for k, then it's true for the next number in line, k plus 1. We assume it's true for k, and then we show it's true for k plus 1. Alright, let's start. 1 plus 2 plus 3 plus all the way to k, and then we're going to go that next step to k plus 1. If that's true, I replace k with k plus 1 here, so that I have k plus 1 times k plus 1 plus 1 over 2. Okay, this is all that previous stuff, all the way to k. All the way to k is equal to this. So now I do that substitution, and I have k times k plus 1 over 2, that's this previous, plus k plus 1, equal to, and let's clean this up just a little bit, k plus 1 times k plus 2 over 2. On the left, let's create a common denominator. So in our numerator here, we'll multiply so that we have k squared plus k over 2. Create our common denominator. That gives me 2k plus 2. So that the left side of my equation is k squared plus 3k plus 2 all over 2. The right side of my equation I need to FOIL. So I have k squared plus 2k plus k plus 2, which is k squared plus 3k plus 2 all over 2. And we have proven our second condition true. So we know that our statement is true. Alright, we are going to look at one final example of induction. We are going to show that 3n minus 1 is divisible by 2, sorry, I left out an I, by 2 for all natural numbers n. So we're going to show that 3n minus 1 is divisible by 2 for all natural numbers n. We do that just like we have been by showing that both of our conditions are true. The first condition that we check is to see if it is true. We're going to show it is true for n equals 1. Well, when we show it is true for n equals 1, we say, alright, if n is 1, then I would have 3 to the first minus 1. And 3 to the first minus 1 is 2. And 2 is divisible by 2. So our first condition is satisfied. That is true. Now we're going to make our assumption. We are going to assume that 3k minus 1 is divisible by 2. And our second condition tells us to show, therefore, excuse me, that 3 to the k plus 1 minus 1 is divisible by 2. So we're going to think about some substitutions here. Well, not really substitutions, but we are going to create an expression that is factorable, okay? I'm starting with 3k plus 1 minus 1, and that is the same thing. I'm going to add in a zero pair. A zero pair is any value and its opposite because they add to 0, like 2 and negative 2 add to 0. So I'm going to say, okay, you know what, I can write this. I can choose to write this as 3k plus 1 to the k plus 1, and then I can say minus 3 to the k plus 3 to the k, because that's just a zero pair. That does not change the value of this statement at all. Alright, so I put in that zero pair, and now I'm going to use my rules for exponents, and I'm going to rewrite this first term as 3 times 3 to the k. Because this is 3 to the first, this is 3 to the k. When I multiply the base, I add the exponents. So this is another way to write 3 to the k plus 1. So I have 3 times 3k, that's the same thing as 3 to the k plus 1, and I have minus 3 to the k plus 3 to the k minus 1. Now I'm going to factor by grouping. So I'm going to group these first two together. And I pull out this 3 to the k. I group together 3 minus 1. Factor by grouping, I pulled out my common factor 3 to the k, and that leaves behind 3 minus 1. And then over here I have plus 3 to the k minus 1. Now, 3 minus 1 is 2. So I have 3k times 2. Let's look at these two pieces. This piece, 3 to the k minus 1, we assumed is divisible by 2. Divisible by 2. That was part of our beginning, part of our assumption. And here we have 3 to the k times 2, which means this is also divisible by 2. Because anything multiplied 2 is divisible by 2. And because of that, we've shown that the whole thing is divisible by 2, and our second condition is satisfied. All right, you see how this is a lot of logic, it's a lot of reasoning, it's kind of a proof feel to it. Different problems are structured differently, you have to use different approaches, but you are always trying to show that both conditions are satisfied.